We can continue. Okay, thank you very much for being patient. We are nearly at the end of this session. Okay, I hope that we by now understand what do we mean by the phase space in transverse direction and the phase space in the longitudinal direction. I tried to draw this on the tablet, but my drawing is not very good. I made a cartoon already. This green particle is the synchronous particle, and when the gun starts, it just emits electron at a very long period of time as compared to the time period of the RF. Okay, so these particles, 50% of the beam is already lost. Okay, and only this part is the stable RF bucket. The bucket I drew on the tablet, it's sort of elliptic, just like the spiral things. Okay,
so in fact, 3/4 of it is lost.
Yes, 3/4 of it is lost. A good RF or the physicist will design careful bunching mechanism. We will discuss it.
But can't you synchronize, the electron generation?
Yes, of course. That's where
So that the loss of the efficiency
is minimized. Those RF guns, the lady was talking about it. They use lasers to ignite only that part of the thing is carried. If you can use grids, this can also help. Yeah, gridded guns and RF guns are meant to reduce this kind of loss. So this was the phase space I was talking. It's P minus phi s. Phi s is the synchronous phase. P is the relative difference. So the particle, the dark green particle, is at the center of the population. Some are lagging in phase, some are ahead of it. So they make a sort of a hook, a sort of this snake, maybe hook, a duck, neck, you call it. This is the shape of the bunch in phase space. Okay, the longitudinal phase space. I come to this fish again. This fish, the eye of the fish is basically the position of the particle, the synchronous particle. Those who are late, they gain energy and they come on the higher side of the energy diagram. Those who are very early, they lose their energy because they are subjected to lesser acceleration. Eventually, they will come to this point. The unstable particles are here. They are not making any part of it. What about those particles which are either very high in energy or very low in energy? They will never make it to a bunch. So you can have bunches, but you're not free to have any sort of electron gun energy. Now, there's another constraint. You have to be limited to the energy of the injection. Energy injection will eventually determine the acceptance criteria for the phase space in longitudinal direction. In longitudinal direction, you have to be at the right phase, okay? You have to be at the right time. That is the other sentence. But you should be able to present yourself at the right energy as well. If you're too slow, you will be lost. If you're too quick, okay, stay here. We're not going to be your family. We're not going to be part of your family. So, not very quick, not very slow, just to be the part of the family, you have to be synchronized. Unless you do it, no chance. Okay, these are some equations. I would I certainly know that you guys can go through it. This is basically what I want to show you. This is the separatrix, the fish. This shape has a certain shape. And the maximum width is when this phase of the wave is synchronous with the phase of with the velocity of the particles. What does it mean? We were talking about slow wave structures. Why we need to slow the waves? We need to slow the waves because the electrons which are coming from the electron gun should have enough time to be the part of that separatrix, be the part of that family. They cannot be injected with very high energy because professor said that the phase velocity of the wave, electromagnetic waves, is higher than the velocity. Light has 8 velocities. The only velocity which we are concerned is the propagation of the energy velocity is the c, 10 minus 8, 10 plus 8 meters per second. But there are other velocities which are equally important. One of them is phase velocity. So this is the phase where we want to stick our particle. If this phase is varying quickly, particle will not have time to stick it to the right time. So this wave itself has to be slowed. The ideal situation will be when the phase of the wave will be similar, or the energy of the particle, in fact, will be similar, same as the wave. Maximum particles will be stick to the accelerating phase. And those who are injected below the energy, they will be lost. If they are very high, they will be lost. So this is basically the acceptance criteria. We call it phase acceptance of the separatrix. Mind it that we are squeezing our boundaries. We cannot have electron gun of infinite energy because the client is limited with the wave which is injected in the first cavity. The cavity where the electron bunching will occur, it has a limitation. So your electron gun must be meeting this acceptance criteria, the phase acceptance criteria. Take a look at this. Take a look at this graph. This is a graph of the beta, the relativistic beta, B over C, of the electrons. I plotted it from, let's say, from few hundreds of keVs to 1 MeV. The range where typical electron guns in clastrons operate is around 100, 200, 150 kilo electron volts. And they're still not very relativistic. It's around, say, for example, for 200 keVs, the beta is 0.7. So 200 kilo electron volt gun is a huge gun. I mean, if you guys have ever saw, designed, or even operated electron guns, you guys can appreciate this thing. This is a huge number. So if the gun has around 100 keVs, so it's roughly 0.55 of the beta. So the acceptance in this case is limited. Let me draw. I draw it in MATLAB using this equation. You guys can also draw it. Say, for example, I have 50 keVs. The window where I can inject is quite small. This is the window where this separatrix, the eye of this separatrix, touches this zero line. This zero line marks the position of the synchronous, where the momentum goes negative. Momentum can go negative, by the way, depending upon the phase, because the momentum is a vector quantity. It depends on the velocity. When the velocity goes negative, so these particles, if they are negative, this is the vector, this is the momentum, and this is the phase. I changed the, I should have mentioned it, but due to lack of time, I could not go. I changed this thing to momentum, but this is the same thing. If you go through these slides, you should be able to have a flavor of how it's done. But in any case, just imagine that you have a particle whose momentum corresponds to 50 keV acceleration. 50 keV acceleration, this is the synchronous particle, the position. And if they are very slow, they can go negative. So this is only the part where I can inject a stable, or I can expect a stable bunching mechanism. What if I increase my energy from 50 to 100 keV? I almost double it. So the value of acceptance is increased. The point where it touches the zero axis is increased. Further, if I increase it further to 150 kVs, 140 kVs, I can have more and more and more electrons gluing to the RF signal. So you have to be patient, you have to be disciplined, and you have to have electron guns with higher energies if you want to have maximum population. Now comes the simulation part. Say, for example, someone has already designed a cavity. For us, this is a buncher cavity, and we have electron gun attached to it. The electrons, when they're here, they are subjected to a certain voltage. It is a very gentle voltage. They are just like rearrangement sort of thing. They are not accelerated a lot. They are not decelerated a lot, but just gentle rearrangements. Few volts to few keVs of energy is imparted in this region. And then they are let go, they are set free in a drift length. Drift, precisely speaking, is a space where there is no field, no accelerating field, no magnetic field at all. Okay? But they tend to go away. I mean, particles due to space charge effects and many other effects, they tend to diverge. So we have to keep them within the limits of this boundary. So we apply solenoid on along the length. Okay. Excuse me. So we have an RF cavity. We inject it with some electrons. We want to experience the effect of ballistic bunching. Ballistic bunching, velocity bunching, phase modulation. These are the same things.
May I ask a question?
Sure, sure.
Do you need solenoid to focus electron?
Yeah.
Okay.
Someone was talking about boring physics codes. Their physics is boring, but unless you know every bit of the physics, you cannot go through the physics design. This is a line which you have to write for Parmela. Parmela is a specialized code written by some guy many decades ago in Los Alamos National Lab. Excuse me, I do my RF calculation in that software. It has a line, and you have to make entries. 0 is a placeholder. RA is the radius of this cavity in centimeters. Out flag means, do you want an output at the end of your simulation? Okay, 1 is yes, 0 is no. So del W is the incremental, is the spread in energy that is embedded in the incoming beam. The incoming beam is not monochromatic. It has a distributed energy. It has distribution of energy. So few EVs of energy are already there. What should be the frequency of the wave that is there? I can take it as a 500 megahertz. This is one of the problems that we are solving these days in our project. And phi 0 is the synchronous phase. The phase of the synchronous particle. Oh, this is a problem. I want to inject my particle at the 0 crossing. the particles are okay. This is sort of a deceiving, I mean, on my part, but I deliberately did it. I injected my particle when the signal is already risen. But now for bunching, I want to place my synchronous particle at the zero crossing. I want you guys to think, we can discuss this as a homework problem. Why, you can write it, why for efficient bunching, you have to put the synchronous particle at zero crossing. Zero crossing is where the field is rising in time. There's a catch. There are two zero crossings. One is the rising electric field, and the other zero crossing comes when the field is decaying. You have to put your particle where the field is increasing in time. That is the zero crossing of our interest, not the other one. Okay, clear? I will write it down in terms of, sorry.
So, I could be very well.
Yes, okay. This, you understand this point, that I want to bunch my beam. Okay, I said that I placed my synchronous particle at a certain positive value of the phase. The field is already risen at some point, but this phase is, for some reason, is not good for bunching, for efficient bunching. I want you guys to think in your mind. So for efficient bunching, I would use this at the zero crossing, the crossing where, imagine this is the wave, and this is the horizontal axis, the time axis. I want to put my particle here instead of here. Maybe I have a wave already drawn. Okay, yes. I want to put my particle here, not here. Why is this? This is the question. I will write it down during the lunch break, and I will share it with the question paper. You guys can have it as a homework problem. Think about it, it's very interesting. So once the particles are, once the problem is completely defined, this is just one line. I have to write a lengthy code for the whole physical problem. I have to define the physics of this thing. I have to define the physics of this thing. I have to define the drift length. I have to define the solenoid. I have to define the injection energy. I have to define how far I want the beam, blah, blah, blah. It's a long thing. It's just like a telephone directory. I don't know if you guys have telephone directory these days, but there was a book which contained telephone numbers, important telephone numbers of every guy in the world. So this thing is literally full of numbers. Every number has a significant physical meaning. Unless you understand this thing, we are lost. Okay. I borrowed this picture from a very good book. It's by Helmut Wiedemann. Suppose that we have particles which are injected in an electron gun. They have a certain distribution, a thickness of energy, but they're distributed in time. Once they come across this RF signal, the ones at the center will remain. Okay, I'm partly answering the question. Or should I not? Okay, so this guy will come here, and this guy will come here for some reason. Think about it, it's very easy. So this will be bunched in time, but the energy distribution is enlarged. So there is a price to pay. The distribution of energy is higher now, but the time frame is squeezed. This is very important. Now this guy, this whole bunch can be presented to a single point for acceleration. For acceleration, I will now present my beam at, once the beam is bunched, this can be the choice of synchronous particle position. But unless the beam is not bunched, zero crossing is favored. The graphs on the left-hand side shows what sort of distances if it will be required for different energies. For example, for 100 kV injection and the subharmonic buncher, the voltages in the buncher, if they are 20, so this is the distance in meters where the maximum bunching will occur. For the same reason, if for the 20 MeV, the value is reduced, something. Okay, this is the result of the Parmela. We can discuss it in detail, but let me quickly go through the results. This is the injection. The electrons with every sort of phase are injected at the input of the cavity. This is the phase diagram. The phase diagram means the phase spectrum where the phase of every particle is plotted with respect to the synchronous particle. Okay, this plot is the spot of the beam, X and Y. I'm not sure, because this is not a very friendly software. This is in fact the same scale. It's a slightly elongated, but you should read the numbers. This is the phase space, which will actually tell us the thing. This is the energy thickness. This is the length of the in time. This cartoon is this guy, the phase and the energy. The phase and the energy, and this is just RMS energy redistribution. So at the injection, the portrait of our beam looks like this. This is the complete longitudinal snapshot of the beam. Okay. After all this mathematics, I assume that this should not be a problem. Okay. Our beam has already interacted with the RF, and now it has just exited the RF cavity. What happens? There is a distribution. The beam is modulated like this. But can you see the population at the start of the peaks and the valleys is higher? Is it the case? And once the drift section is achieved, okay, I also should see that there is not much distribution in phase. But once we let the beam to rearrange depending upon the velocity, this will happen. The phases of the particles will be concentrated around the synchronous particle. Okay, this is what is the signature of bunching. The signature of bunching in phase space is that the phase of the particle is closer to the synchronous particle. Okay, and the beam is much more bunched. The energy they're presented in a very shorter time. But we have two things. We have two things: the upper portion and the lower portion. They have the population has been redistributed. Check. This will be lost. This will be carried away in future. If we plot the same thing in the longitudinal direction, we see that this is the beam, the beta function of the beam, which we just plotted. We have this. These are the two phases. You see, there is very narrow population, and then the population is starting to diverge again. Okay, this is the point of maximum bunching. But if we let the bunch to travel without any interference, it will again start debunching. So the simulation tells us for a certain energy, for a certain physical dimension, there is a limit where you can have a maximum bunch. So you put your next cavity or whatever you want at that point, not beyond that point. So I magnified this thing. This is the maximum bunching point, and then the bunching starts decaying again. This is the phase difference. This is the phase difference, and this is the distance. Remember that in the gun you have very wide band of energies coming through of time coming through. In the cavity, they are rearranged, and then in the drift space, they are bunched depending upon the velocities. Okay, there is a limit of the bunching parameter. Please refer to the early equation. I won't go there again. Usually, if the voltage of the gun is, let's say, voltage of DC, then you can apply up to 50% of the gun voltage as RF modulating voltage. Okay. This is the voltage that is presented by the gun. And in the RF cavity, you cannot have voltages beyond the value of the gun. So it's always around 20% to 50%. This is the limit given to us by the physics. That's what we are discussing this morning. Okay, there's another question. So far, we were dealing with non-relativistic particles. What if the particles have already gone relativistic? Can you think of a way of how is it possible to further bunch them? Because, okay, the particles are relativistic means that they have already achieved the velocity of light. So the particles which are behind me, they will remain behind me. I'm also relativistic. The particles which are ahead of me, I will never be able to catch them. Okay, this is the relativistic thing. Velocities are, unless we do something crazy, we don't want to retard anything. We don't want to. We cannot accelerate them. We do not want to decelerate any particle. We cannot accelerate any further. What is the choice? What can be done to further bunch the particles? Think about it. This will bring us to the end of our talk.
Quadrupole structures to bunch.
Any other answer? Any other suggestion? Yeah, we can use magnetic field, but probably not quadrupoles.
The relativistic electron in the frame, there will be length contraction. So
Yes.
They will feel themselves closer.
Yes, but in the laboratory frame of reference. I'm talking about the synchronous
laboratory.
particle frame of reference.
Time and displacement.
Yes, time and displacement. This is the answer. The particles who are moving ahead of me, I will say, okay, you are very rigid. Go along the path. Spend some more time, unless, okay. So for example, we are 3 people, all relativistic, enter from this point, and our destination is that end of this auditorium. The one who is ahead of me, I will request him to travel to a longer path. I will take a shorter path, and the one who is behind me, I will say, okay, Bridget, you will have an even shorter path than me. So the path variation is what is done in case of relativistic particles. In case of FELs, people do it. Our next thing, I worked there while I was studying. So this is the curious case of 2-beam test scheme. This is the perhaps longest klystron in making. I don't know what is the current status, but once I was at CERN, the scheme was being tested at CLIC. CLIC is the compact linear collider. You cannot, of course, accelerate electrons to very large energies in circular accelerators, so you have to have a linear accelerators. What they do to power the electron beam, this is the electron beam in yellow. the arrows show the increment of the energy. They feed this accelerator, they call it the probe beam, with another accelerator. This accelerator is called the drive beam. It is very high energy, sorry, very high current linear accelerator. What they do is that they take the electromagnetic radiation from this accelerator and feed it to the main accelerator. These are two parallel accelerators. One is feeding the other. This is the two-beam test scheme. Two-beam test scheme is where this beam is feeding it. It's the same principle, the same green equation that we saw. It's a similar equation, nothing else. But here, the case is that the energy of the particles is already very high. For example, when I was there, it was already operating at 300 MeVs. So what they do is they further use a certain scheme to bunch the electrons. How do we do it? We use chicanes, we use magnetic structures. What we do is that we take beam from one LINAC and pass it through arrangement of dipoles. The ones with higher energies will take longer path. The ones, because there is a certain energy distribution. I mean, you cannot have a perfect combination. So one with higher energy will take a longer path. The one with the little bit shorter energy will be taking a shorter path. So they will be bunched, and then bunch is further accelerated. There's a whole lot of mathematics. I'm afraid I will make it more boring, but the thing is that you should appreciate that this main LINAC is driving the accelerating structure. This is the LINAC, this was the accelerator, and this is the short beam pipe. You can, in fact, understand that this is the 13 gigahertz structure. 13 gigahertz structure is they're very small, and the aperture is very small. So you have to, in fact, invent a scheme of quadrupoles to not only confine your beam so that the beam exactly passes to the center of the cavity, and also the longitudinal space is conserved. So that's what is modeled using MATLAB. So we have to have a detailed understanding of the state vector, and MATLAB function using quadrupole, dipole, and all these things can be used to define this scheme. For every particle optical element, we have a matrix. We now know it. We take it into account. We just describe an array of the matrix algebra. We subject it to the input parameters, and when we adjust those, the most precise beam is achieved. In fact, I learned this technique when I was at CERN. We have implemented it at our project, and once this project is extending, we are using even a further version. If this is a very long beamline, which we expect to be with us in a couple of years' time, inshallah. So this is the main scheme of the arrangement of the magnets, and you can change the drift spaces, you can change the strength of all those magnets to have the beam of your desire. So this is our model for tomorrow. Gun with very high current, we need to design this thing. The optics control must be there. The beam transport system should be very efficient. And we have to apply some stable operating conditions in order to have a stable bunch. And we must appreciate mode of operation of optimal performance and reduce beam losses. With these input parameters, we should be able to design an electron source. Remember the first slide which I showed. We have to devise a small thing, but we have to go through all the physics that our client requires. Okay. There's a whole lot of bunch of very useful books. When I started my career as a scientist, my professor gave me this book, Free Electron Physics. I don't know if it is available in print form these days. I have my personal copy which was gifted to me. You guys can make it a copy and share it among yourselves. It's a Free Electron Physics, P.S. Farrago. It's excellent book if you want to study physics. Then there is these are not limited to this collection. You can have as many as possible. It's a very small, it's very thin book. You can maybe understand it in 4 or 5 days. It's an applied charge particle dynamics, particle optics, Helmut Liebel, particle accelerator physics. It's really very tough and useful book. RF principles are discussed here, and this is a very recent addition to the MATLAB programming, particular to accelerator physics. Accelerator physics, I don't know why people are more biased towards MATLAB, but yeah. This guy was at CERN, and now he has published all his work in the form of a book. So I encourage you guys to study. You guys can have a discussion with me if you like. We can discuss the program. I think I have taken a lot of time, but I guess we are well equipped for the design of electron gun. Thank you very much.
So, up to now, the branching effect is based on the dispersion in the kinetic energy of the particles. But there's also the electrostatic repulsion.
Yes.
That effect has not been considered.
Yes, but tomorrow I will discuss the space charge effects further, and we will take into account the theory of that particular effect that you were mentioning, and then we will be better theory.
That will also be part of the
Yes, of course.